Good morning again. In today's class, we're going to cover 4 topics: logical instructions, lookup tables, macros, and we start programming with C. To remind you what we did last time, we wrote a program in assembly. It's going to be probably our last assembly program we write, then we're moving to C. The program was about blinking LEDs connected to port B, on for half a second, off for half a second. And we ran the demo on the board and you saw it working. The learning objectives were here is to learn about the call. So we learned how to do a call for a subroutine. So when you want to execute a set of instructions, instead of writing them again and again every time you need them, you can put them in one place and then you call them. You call them. Call translates into making the program counter go to that place and start executing the instructions. However, the subroutine should include a return instruction at the end to make the program counter go back to the place where it was before the call. This was one of the learning objectives. The other one is doing delay loops. So we learned how to compute the timing of instructions, how much time they will take to execute. And then we learned how to do conditional branching. We use them in a delay loop. Well, probably today we'll do it in C, conditional branching with something else, maybe push buttons. So going to our topic today, and we're going to finish chapter 5. Logical instructions, number 1. And we covered that when we were explaining the instructions, right? And W with F, it does a bitwise AND, right? Bitwise and we showed the difference bitwise versus logical AND. The good thing it's recorded, so I don't have to repeat it. So you can go back to that course when we started talking about, to that lecture when we started talking about the instruction set. So I gave examples. So this is a bitwise AND between the 8 bits in W register and the 8 bits in a memory location in the data memory RAM F that you provide. Then AND literal with W. Here you AND W with a literal, a number you provide in the instruction. Inclusive OR, this is a logic, just OR, but a bitwise OR. W with a memory location. And XOR, W with a memory location, exclusive OR. So we explained these. Oh, well, did we do them here or in class on the board? I forgot. Anyways, if you have any questions about them again, I'm pretty sure we spent a lot of time on them. You can ask me later or in the office hour.
لا دكتور اعملهم اونلاين مش
Okay, great. So they're recorded. Thank you, guys. So these are the logical instructions. They're very useful. And we're going to use them today. The second topic is the lookup tables. And this is a really interesting topic. And when I was like you at school and they were telling us about lookup tables, I didn't believe in them a lot. However, when you go to the industry and see how they're widely used to make things easier and more practical, you would appreciate the value of lookup tables. So let me try to give a small brief example about lookup tables and how they would be used to appreciate them when we start doing them. For example, you're designing an engine controller. Well, should I give something else? Well, that's what I'm good in. Suppose you're designing a controller to tell for the computer, the engine computer, to tell the car how much gas should be injected, okay, when you press the pedal, for example. So one way is you can say, okay, gas, okay, amount of gas equals the how much you ask for the pedal angle, right? You press the gas, right, times a calibratable number, maybe a constant k. Okay, so you translate it proportional. Somebody else would do it in a different way. Well, it could depend. We're talking about smarter cars today, and we want to save gas. So why should we give more amount of gas if you press more? Why you don't need it? Because you're at a certain speed level, and you cannot give more gas if the amount of oxygen, right, that's going to burn the gas is not enough. So you could add another parameter, maybe O2. They call it lambda, the gas to air ratio, but I'm not going to go that deep. Maybe the amount of O2. So if you're or you can add the pressure, right? You can add the current speed of the car. You can add the gyro or accelerometer sensors if it's a new car, or the modern one with gyros and accelerometers readings to see if the car is going uphill or going downhill. All these things could matter in your decision of how much gas you want to mix and burn. Okay, so when the parameters were small, you can add temperature, for example. You can many things. The pressure in the vehicle, the weight, whatever. So sometimes it is easy to develop a simple formula for something that you want and tie it with other parameters. It would be simple, that x would be y air times z whatever plus b. It would be simple, okay? However, sometimes it is more complex than that. So I'm pretty sure all of these things we put here matter in the amount of gas you really need, torque, everything. So, but it's really hard to formulate in a simple formula or have a mathematical model for the relation between several or the different parameters. So one approach to solve the problem is to do calibrations or do tests and figure an optimal value, a good value at certain points. So people use, in this case, something we call lookup tables. So you can say if the temperature, so the inputs, if the temperature and the, let's say, pressure, okay, is, for example, between 0 and 25, and pressure is between X and Y, then the valve opening of the gas paddle should be this many degrees angle, okay? but if the temperature is between 0 and 25, but the pressure is between Y and A, then you know, at a different angle. If the temperature is 50 to 100, and regardless of the pressure, I want the angle to be this much. So, and you can add even more to the lookup table. So if this and this and this, then do this. If this and this and this, then do this. Okay, it's to make things easier when it's hard to formulate a module or a formula to calculate something. Okay, so this is the concept behind lookup tables, and really it is widely used. That people use it in the industry. So if you want to do a lookup table, maybe in C it's easier, right? A lookup table, you just do a matrix, right? And if the indices is this, then the value is this. How to do it in assembly? We'll see it now. Before we start, there was an instruction when we studied the instruction set called return with lateral NW. It's just a return from subroutine. Remember the normal return we studied when we did the call last time? Call a subroutine. Okay, I have to hold this. Call subroutine. Then the subroutine starts somewhere here. You have instructions, and the last one should be a return to make the program counter go back here. If you want to return with a value NW, you can say return with lateral NW 2, for example, or 0, or 1. So when you return, you're going to return. You may check what you returned. Maybe what you return is based on something you did inside the subroutine, okay? So like when you say return 0, return 1, return whatever. Feel free to stop me anytime. So this cartoon shows, visualizes how the lookup tables work, and it's a very good example. So in your main program, you want to look up a value, depending on a value you want. So you know the temperature, okay? And you want to know if the temperature is 5, what is the value for the, maybe, you know, you can go deeper than what I said. You guys studied control, right? If you have a PID controller, the P controller has a KP gain, and this has a KI gain, and this has a KD gain. It could be a constant in many cases. However, in real life, no, the controller gains change depending on other parameters. Maybe when it's really cold, the gains, the PID controller should behave differently than when it's really hot, okay? So, okay, so what is the KP value at temperature 5? You can just look it up, okay? So I send a 5, you return to me something, a 1F if it's 5. If I send you a 6, you're gonna send me a 3. If I send you a 7, you're gonna send me a 67, for example, okay? So you send something, you get it, you get something that is related to it in a way from the lookup table. So how do we implement it in assembly? See what we did here? Move F, sample number, comma 0. So sample number here is, let's say 5, okay, 5. So move F 5, comma 0. So this is gonna move. There is a memory location, move F, right? Move the contents of a memory location. Let's assume it's not 5, maybe to make it different, 52. There's a memory location 52 here. Move the contents of this memory location to what? The direction is 0 to W. So a number in 52 is 5. So take this and put it in W. So after this instruction, W will have 5 in it. Then we call a subroutine called table. It's just a subroutine, but we call it table. Call it whatever. Call it Ali. Call it whatever. Okay? The table is here. The subroutine. Where did we write our subroutine last time? The delay subroutine. You can write this in a similar manner underneath the code. Okay, you call table. So the program counter goes and points here, right? The program counter points to the first instruction. The first instruction in the table just adds W to F to a memory location called PCL. What is PCL? PCL is the program counter low. It reflects the lower 8-bit of the program counter, right? And it is placed in the RAM, right? But it is mapped to the lower 8 bits of the program counter, this one, okay? The 13-bit program counter. So you're adding what's in W, the 5 in this case, to the program counter low. So after executing this instruction, the program counter is pointing to the next instruction to be executed, right? So when this add is executed, the program counter is here, right? So you add to it a 5, so +1, +2, +3, +4, +5. So it's going to point here after the add W to F PCL is executed. This is a return from the subroutine, but return with a literal in W 1F, right? So it's going to return back to where we were after the call here, but with a W holding a value called 1F. See, it is taken back the 1F. So when you executed the instruction, W was 5. Now when you're back, W is 1F. Got it? Now, if you want to do it again, if move F sample number 52, let's say here, okay, and here we have 7, okay, 0. So W after this instruction is going to be 7, okay. Then you do the call table. Then you're here. You fetch this instruction from the instruction is fetched from program memory, decoded, starting to be executed. The program counter points here. Add W, which is the 7, to the program counter value that is here. So this value +1, 2, 3, 4, 5, 6, 7. Then you return with a literal W 67. So when you're back here, the value when you're back here, W equals 67. Okay. If you send a 0, you're going to return a 23. If you send a 1, you're going to return a 3F. So if you want to visualize this table, let me erase this and okay, there should be a better way. Erase all link on the side. Okay. If you want to draw this table as a lookup table, it's going to be something like this. If the value I sent, let it be called X, and what you return is Y. If I send you a 0, you're going to return me a 23. If I send you a 1, you're going to return me a 3F. And this is all in hex. If I send you a 2, you're going to send me a 47. Okay? And so on. Easy, huh? Okay. No answer. Good news, huh?
Yes.
Okay.
طب دكتور سؤال.
Yes. فارس تفضل.
هلا إذا كان بدي إشي يعني مثلا كومبلكس أكثر زي ما مثلا كنت حاط أنت قبل شوي إنه بدي يكون واي ومع زد ومع أكثر من شغلة.
Well, you need to think, you need to, thank you, good question. You need to think deeper. So this is, you return one value. If you want to return 2 values, you may want to think of, okay, moving the values to a memory location tied to what you sent, right? So when you call the table, you say move lateral to W to a memory location F. That's that you add W, right, to indirect addressing mode, maybe FSR, and you go store it in a memory location and the memory location after it if you want several values. So W alone is not going to be enough. So, right? So you may have several instructions that store data depending on what you got in several memory locations in memory, but here the memory locations depend, you calculate, you make it indirect addressing mode based on the FSR and INDF registers, okay, when W comes, and then you return normally. You don't need the return with letter in W because you stored everything in a place. So it's you need to design it differently. This was a very simple one for one value. Okay. Okay. So this is the same example here. This is the cartoon translated into code. Okay. You saw when we wrote our assembly program last time, we said, oh, status equates 0.3, port B equates 6, TRSB 6. Okay. So these things, if you don't want to keep writing them again, you can write them in a file, call it, save it .inc. So put this in a file, save as file, call it whatever, .inc or include or whatever. Then in your main program, you just say include this file. So these will be included. You're familiar with this when you. Okay, macros. Macros is also a nice concept to make writing code look easier. So when we study, so this is a good example of a macro. We have an instruction called move lateral to W, right? When we study the instruction set of a microcontroller. And these are fixed colors. They're tied to the hardware. You cannot add to them or remove from them. What about if you frequently add a lateral to the contents of a memory location? What would you do? You would need first to move the lateral to W, then add W with the memory location, right? So instead, in your program, here's your program. Here you want to add the lateral to memory location. So you need to execute these two things. You need to move the lateral to W, then add W to the memory location. Then you move on. Then you need to write these two lines of code. Then you move on. Then you read to write them again. See, it's a headache, and it's only two instructions. So to do that, you can write something called a macro. And this is, if I want to make it look easier, it's closer to be like directives talking with the assembler rather than, so when the assembler assembles the program, whatever you do here, the macro name is going to be translated into instructions. So you're not saving memory locations, it's saving you some hard time typing or writing more instructions, okay? So you call a macro, call it whatever you want. You can call it something that it looks like an instruction, but it's not an instruction. Move lateral to F. This is just a name. It's not an instruction that you choose. You can call this Ali, whatever, okay? And you tell the assembler that this is a macro, and I'm going to pass to it two variables, one called constant and one called address, okay? What you do with them, whenever you see move lateral to F 3 comma 0x3F, for example, you will take this 3 as a constant, take it to W. So you're going to do, this will translate into move lateral to W3 constant, then move W to F address 0x3F. okay, and macro, and put them here, replacing this one, okay? This is an easy one. Let's do together a simple macro to do maybe let's look at our instructions and see what instructions are not there, maybe. Okay, the instructions were in chapter 4, right? So let's look for did we have add instruction? We did, right? Here. We had add W to F, right? We were able to add the contents of a memory location with W, but we were not able to add, and we were able to add a literal to W, were we? Or not? Yeah, we were able to add a literal to W, but we were not able to add a literal to F, maybe. And this is what we did right now. Or we were not able also to add the contents of two memory locations, a summation. So let's write a macro together to add the contents. If we have 3 memory locations, a memory location X, a memory location Y, and a memory location Z. Okay, and you always do this. You want to add the contents of memory location X plus W plus Y and store the result in Z. So you want to do this, Z equals X plus Y. Okay, so what you can say here, these are just numbers, 2, 3, whatever, and these are addresses, 0x20, for example, 0x21, and this is 0x22. In an example, you can leave them as. So let's do a macro called add A to B, or add, whatever, just, I don't know, call it whatever you want, add. We don't have any add, right? Add. And this is a macro. And I'm gonna pass to it A, comma B, comma C, 3 things. So what we want to do here is to add A plus B and save the result in C. So how would I do it? I would, we can add W to F, right? So one of these numbers need to be moved to W. So we can say move F A, comma 0. So A now is moved to W, right? So W has A. Then we say add W to F, and we need to give the result. W already has A, now F is B, and the result should be stored in W or in the memory location, this one. Let's store it in W, okay? So now here, W is A plus B. Now we want to store it in C, so we can say move W, sorry. Oops. Move W to F, right? C. And then, and macro. So you write this once, up there, down there, with the before the directives, after the directives, doesn't matter. From now on, you can start saying, okay, I want to do this, X, Y, Z. So you say add, you need to give them in the same order, add 0x20, comma 0x21, comma 0x22. Okay, you only write this once, and the assembler will translate it into these 3 instructions. Okay, so it will make it convert it to move f a is 0x20 comma 0, then add wf b is the 21 0x21 comma 0, then move w to f 0x22. Okay, so each time you write this one instruction, it's going to be converted. The assembler is going to convert it to these 3 instructions. So you're not saving program memory in this terms. If you're looking at saving memory, you are saving effort in writing, repeating the same thing again and again. Can we do this as a subroutine and make it just and do a call? Well, maybe, but in this case, these variables, the A, B, C, could probably need to be fixed if you just a call, because a call you cannot pass anything, right? You can use the shared memory. You can have a preset place for these variables. You call something, you go get them, add them, and return the result somewhere else. So it has its advantages. تفضل.
الدكتور احنا بس بنكتب ال add A B C وهو بيعمل هاي الاشياء.
يس، بس انت لازم تكوني قبليها حكيت له شو يعمل، كاتبه هذا الماكرو، شايفي هذا؟ يعني انت لازم تيجي تكوني هون somewhere، يا اما فوق هون قبل هذول، المهم قبل ما تبلش الكود، قبل الاوريجين 0 هون بتيجي بتحكي له add. okay, this is a macro. okay, I'm going to pass to it A, comma B, comma C. B أخذها أزرق. okay, so maybe it's not going to work. Let's call it A1, B1, C1 مثلا. okay, then you do these instructions. What move W to F, right? A1 comma 0 بتكملي آخر شيء بتحكي له and macro. okay, خلاص بتصير afterwards هون بدك تجمعي رقمين هون in the code. You just say add 0x20 0x whatever 21 and 0x22 وخلاص. اوكي، لما يجي يعمل assemble زي ما غير الستيتس هذه وعملها 3 لأنها حكيت له بالدايركتيفز انها تسكويت 3 is going to replace this whole line with all what we write here. okay. Cool. So I hope it's going to be handy if you like writing in assembly. Lookup tables done. Include files, macros done. Okay, great. We finished chapter 5. You know, your book doesn't talk about C, okay? It's going to continue even in chapter 6. Chapter 6 is about interrupts. I'm not going to start it today. It's about interrupts, counters, and timers. And it also, if you look at the book, it continues working on the same thing with assembly, okay? But it's a good time for us. We learned enough in assembly, which it's a good time to move to C, to start moving faster and doing things faster, okay? So I'm going to introduce you to C. And we're going to do a simple example together. We're going to use the board I have that I showed you before. The board is from Microelectronica, and Microelectronica has a development kit that I have. You can download it from their website, from Microelectronica. Okay. But I have shared it with you on our e-learning, and this time it doesn't need permission from me. I just uploaded it because it's not on the Google Drive. It's directly on the e-learning. So if you go to resources, here it is, microC, pick setup. Okay, you just download this and run it, and you will get what I'm going to show right now. these are the drivers. When you get the actual board, it has a programmer, right? You need to program it and move the program to the board. And it has a USB driver, I think. And when you get the actual board, you want to configure it, the drivers are here. At this point, at home, you don't have the board. All what you need is the IDE, so you just install this one, step one, okay? You don't need step two before we go back to school and start using the boards. Tamam. So when you install this, you will have this program, microelectronica microC Pro for PIC, okay? And today I'm planning to do you an example to use the logical instruction and things, and to start using other hardware other than LEDs. Okay. How do I hide this? Okay, and hide this. So this is what you get. On the left side is the controller you want to use, the frequency of the oscillator of that you're using. In our case, it's 8 megahertz. Okay, and just close everything, and this is what you get. We want to start a new project. Okay, you can do this new project, or from project, just do a new project. Okay, let's do a project, a really quick one, to do blinking port B and C, for example. Okay, and then we'll add a motor to turn on, read a push button, and if it's pushed, we turn on a motor, and if it's not, we turn off the motor. So we run new project, standard project. Next, now you give it a name. This is demo 4, starting with C. I don't know if so. Okay, you know what? Demo 4 C program, blink, whatever. And I want to save it to my same folder that I will share with you later. So we create a folder here called the class demo 4, make a new folder, class, and I share these demos with you. They are on e-learning. I also put them. C program, blink. Okay, simple one. Okay, and okay. Next, and we provide we choose our hardware here. It's the 16F877A, and my clock frequency is 8 megahertz. This is the one I have on my board. Okay, if you may have something different. Okay, next, cannot contain legal characters. Illegal characters. هاي الشحطات مش قابلها. So I'm gonna remove them. The project name. خلاص, just keep it. Demo 4 C program link. Next. Okay, add, if you have other files you want to add to the project, you can do that, or you just finish. Okay, now this is what we have. A simple empty main loop. See it? What do we want to do? We want to blink port B and C. Okay, here this compiler has the includes in the background. I'll show you how you're gonna get them. But these all the special function registers are known to it. So when you say port B, the compiler will understand what is port B. Okay, so a real quick one. So we are at bank 0, memory location bank 0. I'm sorry, RAM bank 0. To set the direction of port B and C, I want to make both B and C blink. I need to go to bank 1, and if you say TRISB, it will understand it. Okay, but we're learning. So we need to go to bank 1, access the direction registers of port B and C. So this is what we're gonna do. This is what we're gonna do. We're gonna first, and I'm gonna do it on 2 steps because today we still have 9 minutes left. So today we'll do this, and next time we add part 2. So I'm gonna have port B here. I'm gonna set it as output. Well, to build on it next time, let me do it عشان ما أردش أعدل. So we will have port B 0, port B 1, 2, and 3, the first 4 bits defined as input ports, input. So I can connect them to push buttons later, okay, input. These are input. Then port B 0, 1, 2, 3, okay, 0, 1, 2, 3 are the first, then 4 down to 7, port B 7, I want to define them as output. I'll configure them as output and connect to them LEDs, okay. Also port C, I'm gonna do, I'm not using port A yet because I have a reason. Port A is shared with the analog port, so their default is analog, and to change them to make them digital, we need to access the analog digital converter registers, and we're not there yet. So pretend that port A is called C, okay, for now, and 1, 2, 3, 6 until for port C7, okay, and I want to connect make them output and connect LEDs to them. Okay, what did I do? And make them blink. But let's do the blinking when B is on, C is off. So the most 4 significant bits of B and the 8 pins on C. Next time we will add somewhere here a motor. Okay, a motor, but it needs we do it later. We're using an NMOS or PMOS transistor, whatever I have, and with a push, when a push button, we connect here as well. Okay, phase 2. You turn the motor on. We'll do something here to turn on a motor. Okay, but let's do the blinking part and delay part for now, because what is this? Okay, so to configure the direct, we need to go to bank 1. How do we go to bank 1? We make bit number register equals to what? To 1, right? This is the status register. I'm gonna use logical instructions, please. And when I was teaching the lab last semester, I figured out that many of the students rely on the libraries and what's on there. They just say status dot bit 5 and the equal. How is that done underneath? They don't know, and that's unfortunate because we are engineers. We are not hobbyists. Okay, we need to understand what's going on. So if this is bit number 5, and I want to make this bit a 1 without touching anything else, just leave everything else as is. Don't touch anything else. How do I do this? If you want to make a 1, you can do an OR, right? If you OR everything with 0 except this with a 1, everything will stay as is except this bit will become a 1, right? So we need to OR the status register with 1, 2, 3, 4, 1, 2, 3, 4, and the bit 0, 1, 2, 3, 4, 5, 6, 7, and this is to make a 1. So everything, so we want to OR the status register with 0, 0, 1, 0, 0, 0, 0, 0, and this is equivalent to what? 0x, this is a 2, right? And this is a 0 with 20 hex, okay? So if you OR the status register with 20 hex, you are selecting bank 1. Okay. So I want to go to bank 1. So I say or here, status register equals register equals status register, not logical or, bitwise or, okay, bitwise or, with what? 0x 20 hex. Now here we set bit 5 in status register, which is equivalent to select bank 1. Tamam. Now we're at bank 1. I want to make B, the lower 8 them input ones يعني, 4 bit I want to make them output. So I put in TRISP 0x. What's going on? 0x0 F. So lower 4 bits.
دكتور مش بالسي دبل داش عشان قصدي دبل داش عشان الكومنت.
Yeah, the comment is not a semicolon here. Yes. Lower 4 bits of port B are input. Higher 4 bits are okay. For TRISC, I want them all to be output. 0x output is right. So port C is, then we want to is this bit a 0. I want to make this bit a 0, everything as is. What do I do? If I AND everything with ones, except this one for 0 with zeros, everything will stay as is, except for this one. It's ANDed with a 0, it will be a 0, right? So I want to AND status register with what? With 0x, this is a D, and 0, right? D0. So I say status equals status and ampersand with 0x D0. Here what we did, D0, right? Clear bit 5 of status, which means select bank 0. This is a comment, of course. It's like we need to continue this next time. Until then, we still have to. Okay, now we're back to port to bank 0. Initially, I want the تفضل يا قيس.
بس ليش ما غيرنا لا قيس، ليش ما غيرنا البت لحالها الخامسة؟ البت الخامسة لحالها. ليش ما عملنا اند مع
غير لحالها؟ هلا في ناس اصحابك بيعمل ستيتس هيك ستيتس دوت بت او I think this is the format. I'm not very sure because I don't use this format. That is see ولا this dot في بالlibraries صوت بيقطع. still بيقطع كلكم ما حداش سامع.
هيك صار كويس. هلا رجع.
صوتكم بيقطع والله. Okay, you know what? بلاش طيب. Next time is over. I'm gonna stop the recording and we'll continue it next time. If you want to stay, speak have a bad quality recorded. Let me stop the recording and we'll continue next time.
دكتور عادي سؤال.
يس صراحة بس أنا يس تفضل recording still recording.
Yes, still recording.
Anyways, the 15 minutes we'll continue next time. Thank you everybody.